Okay, the Bohr theory of the hydrogen atom. First question is, what is the difference between a continuous spectrum and a line spectrum? Most light sources, natural light sources, if you take the wavelength versus the intensity, you'll find that there's some sort of maximum wavelength, but that pretty much every other wavelength of light is present in this graph. So if you look at sunlight, and you were to map out the wavelength versus intensity, there would be some areas that would be higher than others, but every wavelength of light would be represented. So this is continuous. But then line spectra of elements, when you take a pure element and let it absorb energy and emit energy, it will give off light or absorb light in very particular wavelengths. And, I draw it like this because that's what it actually looks like. It is an actual Gaussian curve. But when you look at a wide range of wavelengths, they look like lines. And if they can be so tight, in those curves can be so narrow that they do look exactly like lines. So this is the difference between a continuous and line spectrum. These are all wavelengths present. Only certain wavelengths present. Why do hydrogen atoms have line spectra? And all elements do, but the one that we talk about in this chapter is hydrogen. It has line spectra because the energy levels are quantized. That is, they are discrete energy levels, which was, at that point in time, was something that hadn't been seen before. It seemed that energy, a bulk of material, could give off any wavelength of energy depending on what you wanted to put into it, or how hot it was, or whatever was allowing it to emit energy. When it did emit energy, it gave it off in every kind of wavelength. But when you took a particular element and isolated it, you'd find that it had this line spectra, and that's because there are only certain energy levels, and what's happening when it emits energy is you have an electron at a higher energy level and it drops to a lower one. Well, it can only drop to 4, 3, if it's in energy level 5, it can only drop to the 4th, the 3rd, the 2nd, or 1st energy level. So those 4 transitions, we can draw them all. Those 4 transitions will give up 4 types of energy, 4 wavelengths of light. There's nothing else in between. So when you look at all these transitions that hydrogen has, it's just you're going to have 4 little lines, very, very tight lines, because it's a very exact, or very precise amount of energy between those levels. Now, what are the values of the first 3 energy levels for hydrogen? Now, the first thing is that we don't normally deal with just the energy of one level. We deal with the energy of transitions, but Niels Bohr came up with the equations that govern the energy levels. This is the Rydberg constant. Make sure I got the just make sure I have the right value. 3.179 times 10 to the minus 18 joules over n squared, n being the energy level. So I did these out beforehand just so that you don't have to watch me punching all these into the calculator. For n is equal to 1, we'd say E sub 1 is RH over 1 squared, which is minus 2.179 times 10 to the minus 18 joules over 1 squared. So that is minus 2.17. That's a pretty trivial one. But when n is equal to 2, then E2 is minus 2.179 times 10 to the minus 18 joules over 2 squared. and this becomes minus 5.448 times 10 to the minus, this should be 19, minus 19 joules, and then n is equal to 3 is minus 2.179 times 10 to the, no, this should be 18, and this would be, yeah, that'd be 19 because we divided by 4, sorry. Just thought I had missed something there. And then 3 squared, and so this would be minus 2.42 times 10 to the minus 19. Yeah, that does make sense. So that should be minus 18. Now, a couple of things. Notice that it's a negative value. A negative value means that, remember, energy is always a positive value. So when you have a negative attached to an energy, it means something. It's telling you something about that energy, which is always positive. So negative energy in this context means the electron is part of an atom. Positive energy means that it is free. So when you have a negative energy, when we're talking about atoms, that means that it's part of the atom. It's trapped inside of the atom. But you can see that as we, n has no upper limit. So if we made n equal to 1,000, then this would be 1,000 squared on the bottom, and we'd end up with 10 to the, this number times 10 to the minus 24. As we add in more, we go to higher and higher n. So as n increases, the energy tends to 0. At 0, that's when the electron is no longer attached to the atom. It's free to leave. So, but there's no upper limit on the n values. But you can see that what should happen is, since we start out with the largest negative number here, and then we keep dividing by the next higher integer squared, that the energy levels get tighter and tighter together. Until when you get up to n in the hundreds, it becomes a continuum. It's hard to see the difference between the energy levels. And then here at n is equal to infinity, we're right at the point where the electron is about to leave the atom. So it doesn't just keep going up indefinitely. Because this number gets larger on the bottom, we keep getting closer and closer to 0. And no matter how large n is, we can never get above 0. It's always going to be a negative number. It's never going to go to positive, and we're always tending towards 0. So negative means that we're part of the atom, positive means that it's free. Okay, so now this is what we're normally going to be dealing with, is finding the wavelength of light due to a transition inside of a hydrogen atom. And the equation we use, I'm going to try to write it, see if this might be, yeah, in this case it's easier to use this smaller or finer point. This is the equation that we're going to use. We have the wavelength, 1 over the wavelength of a transition is equal to the Rydberg constant over hc. And then in the parentheses we have the final energy level minus the initial energy level, 1 over the final energy level squared minus 1 over the initial energy level squared. And those are going to be integers. So if we put in our values that we don't know the wavelength, so it's going to be 1 over the wavelength, the Rydberg constant, so this is going to be 2.179 times 10 to the minus 18 joules over 6.63 times 10 to the minus 34 joules seconds. That's joules times seconds, not joules per second. And then we have this. And then we have 1 over the final, it goes from n is equal to 4 to 2, so this is 2 squared, or 1 over 4 squared. And we see that joules cancel, seconds cancel, and then we're going to end up with a number that's going to be 1 over meters per second. So once we're done with this number, we have to flip it to get the wavelength. So when you do this out, let me just do it here real quick. And then we have this. Okay, and then times 2. And I'm not going to do out every step here. Okay, so 1 over the wavelength ends up being 2.05 times 10 to the 6th inverted meters. If you've carried out all of the calculations correctly, and then you should end up with meters on the bottom. So if you take the reciprocal of both sides, we end up with 4.87 times 10 to the minus 7 meters. You got to do that last step. This happens all the time on the exams where the student ends up with this. Well, they end up with wavelength being equal to this number. It's 1 over the wavelength, so you have to flip it when we're done. Now, we've gone from a higher energy level to a lower energy level. We went from 4, so n is equal to 1, 2, 3. I didn't do a great job. These should be getting closer together, but that's okay. Just want to show that we started in n is equal to 4. We dropped to n is equal to 2. So if that happens, you go from a higher energy level to a lower energy level. It must give off light. And so energy was emitted. And so we have, sorry, FedEx guy just knocked on the door. I can see him from this window. Oh, do I have to sign something? Nope, no, he just left it. Okay, so what is the wavelength of light associated with the transition from n is equal to 3 to n is equal to 12? So same thing. Same kind of thing, I should say. We want the wavelength again. Now, if they wanted the frequency, there's an equation in your book that allows you to find the frequency too. And let me just write this out first. Here's the equation that I will use. And for my exams, you'll need to know the equation. So I'd say just memorize one of them, because we can also use this equation. You can see that they're definitely related. This is h nu here rather than 1 over lambda. The reason I use this one is because the wavelength is what you normally want to find. The wavelength of light is the thing that most people can get their mind around, and it's the type of characteristic of light that people like to see. When you say frequency, you say the frequency of it is 10 to the 15 inverted seconds. That doesn't sit very well with most people. But if you say the wavelength is 433 nanometers, ooh, that's nice. So you can use this, and there's no reason, and this is also equal to energy, but there's no reason to memorize both of these equations. Memorize one, because once you know the wavelength, you can use our earlier equation to convert to frequency, if that's what's being asked for. So we have the wavelength. I'm going to go a little bit faster here, just to make sure we have time. And this is 6.63 times 10 to the minus 34 joules seconds. And then we have the final energy level is 12. The initial energy level is 3. Nice thing is, if you mix these up, all you'll get is a change in sign. But be careful. When you get this all said and done, you end up with 876 nanometers. I should say negative. Now the negative sign that you get just indicates which direction the energy went, so I always leave it off, because it's just what we can say is that it's this wavelength of light that was absorbed. If you went from n is equal to 3 to n equals 12, that means you put energy into the system, so light was absorbed. So if they ask, is it a light emitted or absorbed, you can tell from your n values, rather than having to wait till you get all the way through the calculation. Now here's one that's a little tricky. As the light is emitted from a hydrogen atom, it has a wavelength of 487 nanometers. If the electron that emitted the light was initially in the n is equal to 4 level, what level did it drop to during the transition? So this time, we know the wavelength. They want to know one of the energy levels. So a little trickier. So this is going to be 1 over 4.87 times 10 to the minus 7 meters. That will be on this side. Then we have 2.179 times 10 to the minus 18 joules over 6.63 times 10 to the minus 34 joules seconds. Then 3.00 times 10 to the 8th meters per second. And then 1 over the final, okay, so if it was initially in n is equal to 4, we know that. What we don't know is the final wavelength, or final energy level. So to save time, I mean, it's just algebra here. You have to work everything through. Get rid of those. Notice the meters cancel on either side, which they should because n is just a number. And when you get done with it, you're going to end up with NF is equal to 2. And actually it comes out to be like something like 2.0002 or something like that, but it has to be an integer. So when you're done, you have to round to that integer. So it's just a lot of algebra at this point, so I'm not going to spend a lot of time on that, especially since we're running out of time. We have to be done in 20 minutes here. Then this last one, I'm not going to do out at all because the wavelength is given. It's one, it will be this if you change it to meters. And then we have n is equal to, was initially, this is 5. And you know the constants, and you plug it into our equation, and your final level should be 3. I know it's really quick, but I'm telling you the answer. You set it up just like the last one. And this would be just an extra one to do in case you want to give a little practice. But you should see the basic idea that we're just trying to solve for n in this case and the previous case.